Engineering is about making ideas into reality. For most of its history, the process of art to part has been about drawing and interpretation. But in the digital age, a rendering of ideas is the start of a holistic approach to making things. The new products engineers make are so complex today that digital processes aren't optional, they're essential. Autonomous vehicles are an excellent example of a highly anticipated technology that can't be developed with traditional CAD methodologies. In this series, we'll explore how new capabilities offered by MBSE, simulation-driven design, digital twins, AI, the Internet of Things, and PLM converge to enable engineers to build a low-cost, high-value future exemplified by self-driving cars. Data is embedded in modern products, but also surrounds them. Even the simplest of consumer goods involve layers of interwoven systems embedded with information. Product design encompasses information from multiple engineering disciplines and runs in parallel to the physical product's lifecycle, from initial concept to final inspection and eventual disposal. Autonomous vehicles are the poster child for complex products that are largely defined by data. All modern vehicles, autonomous or not, are built around the core technology of a chassis that carries occupants and vehicle support systems. Those systems include mechanical propulsion, suspension, passenger comfort, and safety systems. Increasingly, networks of sensors and actuators are being added to the mix to deliver everything from selectable ride control to internet connectivity. Controlling everything are microprocessors, a large and growing proportion of the vehicle's bill of materials. As code-driven systems take over more of the functions of previously electromechanical devices, complexity increases drastically, creating a serious dilemma for product designers and engineers. The conventional build, test, iterate methodology can't function with the multiplicity of state variables, differential equations, and edge cases presented by modern designs. MBSE corrals complexity and allows engineering teams to aim high in the design process while meeting cost and time-to-market constraints. The autonomous vehicle design process begins by defining requirements. Who and what will the vehicle carry? Where? How far? How fast? And at what cost? There are similarities and differences between taxiing passengers around a busy highway and maneuvering a tank on a battlefield. The use cases will dictate multiple aspects of self-driving hardware and software. Integration between systems and design teams is key, and the ability to track and control design data as systems evolve must be implemented from the first renderings. Using MBSE, products begin as a live model that updates throughout the design process in a way that ensures that every stakeholder is current with every design revision. That concept of data continuity is called the digital thread. MBSE experts refer to a single source of truth, a simple expression for a difficult problem. A century ago, a locomotive could be fully described with 700 renderings. A modern passenger car would require 30,000 or more renderings just at the component level, not including tooling or assembly drawings. The additional systems required for autonomous driving add complexity at the component level, but must also interface with electromechanical systems that drive, steer, and brake the vehicle. Simply, CAD isn't enough. Consider a LiDAR scanner. The autonomous driving team needs to position the sensor for a wide field of view, minimal interference from the vehicle's structure, and protection against dirt and damage. The chassis team needs a smooth, aerodynamic shape to minimize wind resistance and feed those gains back to the powertrain team. And optimal LiDAR mounting may have a serious drag penalty. CFD and testing may help find a compromise, but how does that sensor relocation affect factors like wiring harness routing or power distribution? System-wide simulation is needed to ensure that every stakeholder sees how every design change impacts the overall vehicle. At the software level, extensive simulation is needed to explore the edge cases that will define success and failure from a safety perspective. When a person darts in front of a self-driving car, the problem is environmental, computational, and mechanical. The ability to feed boundary conditions and edge cases through a distributed design team means that an engineer developing brake systems can factor in previously unconsidered variables, like the latency within AI systems, and that's just one example. With simulation-driven design, engineering teams can leverage tools like FEA and CFD with sufficient time to optimize assemblies before designs are locked down. In the future, generative design will likely optimize and consolidate components in response to those simulations. In the present, the runaway train that is the modern design process can only be controlled by engineering software that delivers a single source of truth everywhere, all the time. And for autonomous vehicles, the process won't end when the car rolls off the line. The entire life cycle of an autonomous vehicle, from its earliest conception to the time it drives itself to the scrapyard, will be continually captured using MBSE models fed into product lifecycle management systems. In the future, that self-driving car will likely predict when it has reached the end of its useful life and then retire itself. MBSE isn't the destination, it's the starting point as engineering transitions to a new generation of virtual and highly automated processes. There's still a long road to travel to develop an autonomous vehicle, and on the next episode, our stop is the digital twin.